space is vast, but tonight we're going to fold it into a single, daring question. What if our entire universe lives inside a black hole? Picture an event horizon not as a wall, but as a one-way door. Beyond it, gravity squeezes matter and light so fiercely that our usual rules go wobbly. Some physicists think those extremes could seed new baby universes with their own space, time, and cosmic history, maybe even ours. In this episode, we'll unpack how black holes work, why singularities cause headaches, and how ideas like white holes, loop quantum cosmology, and the holographic principle try to make sense of it all. If this kind of thought experiment stirs your curiosity, you're welcome to like and subscribe. Then, settle in. We'll begin at the event horizon. The event horizon is the boundary that makes a black hole, an invisible one-way line where escape ends. Beyond it, gravity grows so strong that nothing, not even light, can turn back. Some researchers go further. The core may not only tear matter apart, but also trigger a rebound that opens into a new region of space and time, a baby universe. In that view, crossing the horizon is less an ending than a handoff, which leaves a quiet question on the table. Could our own cosmos be the inside of such a black hole? Before anything meets the center, there is a boundary that matters more than any surface in space. It is called the event horizon. It is not a wall and has no texture. If you were falling toward a very large black hole, you would not feel a bump or see a flash as you pass it. No sudden pressure change, no heat. You would glide through an invisible line. Yet the physics on the two sides of that line are not the same. Outside, paths can still lead away. Inside, all paths aim inward. The event horizon does more than hide what lies within. It blocks information from leaving. Anything that crosses the horizon light, particles, energy, the fine details of what an object was, cannot send a message back out. From the outside, there are no clues about the shape, composition, or history of what fell in. This point cuts deep because physics is built on the rule that information is never truly lost. When a log burns, the atoms and energy spread into ash, smoke, and heat. The details change form, but they do not vanish. Black holes seem to challenge that rule. Seen from afar, a black hole simply grows heavier and its gravity stronger. What exactly went in and how stays hidden? Time also bends near the horizon. To a distant observer, a falling object appears to slow as it approaches the edge, fading redder and dimmer, almost as if it freezes at the surface. To the traveler who is falling, time feels normal. The crossing takes place, and the journey continues inward. Two views of the same event exist at once. Outside, motion seems to halt. Inside, it does not. This split invites a hard question. If observers outside can never access what happens beyond the horizon, what counts as real for them? Physics predicts the future by using present information. But the moment matter slips past the horizon, that information is removed from the outside world. The universe is then influenced by something it can neither see nor measure. These puzzles led to an idea known as the holographic principle. In simple terms, it says that everything inside a black hole could be encoded on the horizon's surface, the way a flat pattern can project a full three-dimensional image. The horizon would then act like a storage surface for information, keeping a record of everything that fell in, not as objects, but as data written on the boundary. This is a bold way to rescue the no information loss rule. It is not yet proven, but it offers a path to make sense of the black hole's strange bookkeeping. No one has photographed an event horizon itself. What we have seen is its shadow. In 2019, the Event Horizon Telescope revealed a bright ring with a dark center in a distant galaxy. The ring is light from hot gas, bent by extreme gravity. The dark center is the region where light fails to escape. That outline marks where the horizon must be. The image is powerful because it shows absence, a shape cut from light by gravity. To understand why this happens, we go back to Albert Einstein's general relativity. In this theory, gravity is not a pulling force in the usual sense. Mass and energy bend the fabric of space and time, together called spacetime, and other things move along the curves. Picture spacetime as a flexible stage. A small mass makes a small dip. A large mass makes a deep well. The tighter the mass is packed, the steeper the well becomes. On Earth, the bending is mild. It is enough to keep our feet on the ground and to bend starlight by a tiny amount. Our satellites even need clock corrections because time runs a touch faster high above Earth than at the surface. Without those adjustments, GPS maps would drift. A black hole is space-time pushed to an extreme. The well is so steep that all paths at the horizon point inward. From outside, time appears to slow as you approach it. At the horizon, it seems to stop. This is not a trick of the eye. It is how clocks behave in curved space-time. Deeper still, light itself is trapped in a special orbit. At a certain distance, called the photon sphere, light can circle the black hole in a loop. The orbit is thin and unstable. A small nudge sends the light out to infinity or down toward the hole. The photon sphere is a direct sign of how hard space-time is being bent. Once inside the horizon, the rules tighten further. Space and time, which we treat as separate in daily life, trade roles in a precise way. Moving forward in time becomes the same as moving inward. There is no path that leads back out, just as there is no way to make your personal time run backward. The geometry itself forces a single direction, toward the center. Einstein's equations allow other odd shapes of space-time near black holes, especially when rotation is involved. A spinning black hole is called a Kerr black hole. It drags space-time around with it, a process known as frame dragging. Near the core of a fast-spinning hole, the twisting can be so strong that the math permits closed time-like curves. A time-like curve is a path that a traveler could follow while always moving slower than light. If the curve closes, the path loops back to where it started. In principle, this could mean returning to an earlier moment. These loops do not need a time machine. They are features that can appear in the geometry itself. Do such loops exist in nature? That is not clear. They may be blocked by deeper laws, by quantum effects, or by the messy, turbulent matter that real black holes swallow. The universe may also be too short-lived or too noisy to let them form in a clean way. Even so, their presence in the math reminds us of how flexible space-time can be under stress. There is another possibility drawn from the same equations: wormholes. A wormhole is a tunnel connecting two regions of space-time through a narrow throat. In principle, a traveler entering one mouth could exit somewhere else, or somewhere else. In practice, wormholes collapse unless something holds the throat open. The something would need properties unlike normal matter, negative pressure, or other exotic features that have not been observed in bulk. Still, the solutions exist on paper, and they hint that a black hole's deep interior might be more complex than a single point of infinite density. In some rotating or charged models, what looks like a dead end can be replaced by a bridge. Under those conditions, crossing a horizon might be less like falling into a pit and more like sliding onto a hidden roadway. These ideas, holographic storage, photon spheres, time loops, and wormholes, grow from the same foundation, the way mass and energy curve space-time. They help us think about what an event horizon means, both as a physical boundary and as a limit on knowledge. Whether our universe is inside a black hole is still an open question. The math leaves room for it. The observations do not rule it out or prove it. For now, the horizon remains what its name suggests, the farthest line of sight, while the space beyond it keeps its quiet. That limit is not just abstract. Rotation shows how boundaries become active. A spinning mass can drag space-time itself, and the effect is clearest next to a rotating black hole. Around a rotating black hole, space itself does not sit still. As the hole spins, it drags the fabric of space-time around with it. This effect is called frame dragging. Close to a fast spinner, the dragging is so strong that anything nearby is forced to rotate in the same direction, even if it tries to hover. Up and down, left and right become slippery ideas because the grid we use to mark directions is twisting under our feet. Time also begins to behave in ways that do not match daily life. As you move inward, the clean rules of geometry fade. Distances can lose clear meaning. Time knots together with space until the usual idea of motion, of going from one point to another, no longer works by simple steps. The equations that describe gravity allow this. When pushed to their limits, they show a world where geometry is active and changeable, not a quiet stage. Near a black hole, the stage can curl into loops, spirals, and folds. A straight path can bend back toward its start. Time, which outside flows one way, can form cycles in certain extreme setups. The event horizon is the edge of access, not the edge of possibility. Beyond it lies a region where geometry can take forms we do not meet elsewhere. The deep interior may be a place where space folds on itself to make shortcuts, where clocks do not agree on a common pace, and where the basic structure of reality is forced into shapes by immense gravity. In the spinning heart of a Kerr black hole, the math even allows paths that loop into the past. Some solutions include tunnels that join far-off places, or even different moments in time. These are not claims about what we will travel through. They are consequences of the same formulas that explain gravity on Earth and the orbits of planets. All of this stretches what we think gravity can do. It is not only a pull that keeps us grounded. Under extreme conditions, it reshapes the rules that space and time must follow. Even if no personal probe could survive such a journey, the mathematics sketches scenes that push our imagination. The photon sphere where light can orbit, the event horizon that blocks escape, the twisting of space-time by rotation, the possibility of closed time-like curves, the hint of wormholes each emerges from Einstein's field equations when matter is dense and gravity is strong. At the center of this picture sits the idea of a singularity. Many imagine it as a tiny dot with no size and infinite density, a place where everything that falls in is crushed beyond recognition. It is a vivid image, and it seems to match the drama of a black hole. But the word singularity may be less a thing and more a sign. In physics, when a calculation returns infinity, that usually means the model has been pushed past where it works. Infinity is a warning light, not a measured object. In general relativity, the singularity appears where space-time curvature grows without limit, and our equations stop giving sensible answers. That point is placed at the very center of the hole, where all infalling matter is thought to end up. Yet general relativity is a theory of the large. It handles planets, stars, and galaxies with grace. It does not include the rules that control the very small, the domain of quantum mechanics, which governs atoms, electrons, and smaller pieces of matter. Inside a black hole, both sets of rules should matter at once. Gravity is extreme, and quantum effects should be strong. Today, we do not have a single framework that unites these two pillars. So when we speak of a singularity, we are likely pointing at a gap in knowledge. It is not a physical pinprick we have found. It is a question mark where our best tools conflict. This gap leads to hard questions. What becomes of matter and energy that fall in? Do they shrink without end? Do they vanish from our universe? Could they reappear somewhere else, perhaps far away or in a new region of space and time? Our present theories cannot yet answer, not because answers are forbidden, but because the math we need is unfinished. Many physicists expect that a complete theory of quantum gravity, one that blends space-time curvature with quantum rules, will erase the singularity from the final picture. In such a theory, gravity may not be a smooth curve at every scale. Space and time might be built from tiny units, similar to pixels that make a digital image. If there is a smaller scale, collapse could stop before reaching infinite. What looks like a dead-end point in current equations could be a complex quantum structure with new behavior. Loop quantum gravity explores this idea by modeling space as a network of tiny loops. In that view, collapse meets a kind of quantum pressure. Instead of sinking to a point, matter may reach a minimum size and bounce. The end becomes a new beginning. String theory takes a different route. It suggests that the basic building blocks are tiny vibrating strings, not point particles. Under extreme conditions, strings can change their modes, new particles can appear, and extra dimensions can play a role. What we call a singularity might then be a place where new rules take over, not a breakdown of nature. These approaches disagree on details, but they share a key message. A singularity is probably a marker showing where our map fails. The same caution appears when we look at the start of the universe. The equations of general relativity point to a Big Bang singularity, a moment of infinite density at time zero. Most researchers now think the early universe was instead a state of extreme heat and density, where quantum effects were crucial. By analogy, the centers of black holes may be quantum-dominated regions we do not yet know how to describe. Observing the center directly is beyond reach, so we turn to signs at the edge. We read the behavior of hot gas near the horizon. We track the orbits of nearby stars. We listen for gravitational waves, the ripples in space-time that ring out when black holes collide. Those waves carry a record of mass, spin, and distance. We also study images of black hole shadows. In 2019, the Event Horizon Telescope showed the dark silhouette of the giant black hole in galaxy M87, wrapped by a glowing ring. Such data test our theories where gravity is strongest and help narrow the models that might replace the singularity with something real. There is a deeper issue tied to singularities as well. If time ends at a point, what becomes of cause and effect? Does before still make sense near a place where time has no path forward? General relativity does not answer. It was not built to. These questions are not reasons to give up. They are directions to look. They tell us that the laws we have work across a huge range, yet there are corners where new ideas must take the lead. Black holes, then, are more than graveyards for matter. They are stress tests for our best physics. They show that space and time are flexible, that information and geometry are linked, and that our theories must agree where the very large meets the very small. Each new observation, each wave detected, each sharper image adds a piece to the puzzle. The singularity remains an enigma for now, but it is also an open invitation to refine our tools and extend the simple, universal rules we seek. To sharpen those tools, we have to study black holes across their range, mass, origin, spin, and charge, because variety is where theories show their edges. From far away, a black hole looks simple, a dark sphere that swallows light and matter. That plain face can hide real variety inside. As with stars that come in many kinds, black holes may differ deeply by size, origin, spin, and charge. The glowing disks we sometimes see around them are only the outer signs. The interior, which we cannot observe directly, may tell very different stories. The clearest split is by size. Stellar mass black holes are the small ones by cosmic standards, formed when heavy stars die and collapse. They weigh a few to a few dozen times the sunday. Their horizons span only tens of kilometers, tiny compared to galactic scales but deadly up close. Near such a horizon, gravity changes so sharply over short distances that a falling body would be stretched from head to toe. This effect is called spaghettification. In small black holes, the stretching can become severe long before any traveler nears the center. Supermassive black holes live at the cores of galaxies and can be millions or billions of times the sun's mass. Their horizons can be as wide as a solar system. The strange twist is that, right at the edge, the pull can feel gentle. The difference in gravity between head and feet is small there, so a person or a probe could pass the horizon without feeling a snap. Deeper inside, the forces grow and the calm ends, but the first crossing could be quiet. This contrast suggests that the inner layouts of supermassive holes might allow matter more time to interact, to orbit, or to heat and cool in complex ways before any final descent. Some models even hint that new kinds of physics could appear in those vast interiors, patterns that do not form around smaller holes. Origins may matter as much as mass. Not all black holes need a dying star to begin. Primordial black holes are a proposed class that could have formed in the first moments after the Big Bang, when the young universe was dense and uneven. In that chaotic sea, a region slightly heavier than average might have collapsed on its own. Such holes could range from asteroid-like masses to far larger ones. If they exist, quantum effects might shape them more strongly than classical gravity does. Some may have shrunk through Hawking radiation, the slow leak of energy that lets black holes evaporate over immense times. Others might endure, and could even make up part of dark matter. Their insides, if we could describe them, might be ruled by jittery quantum fields rather than smooth curves of space-time. Spin and charge add more layers. The simplest black hole, called the Schwarzschild solution, has no spin and no charge. Its idealized interior ends at a central singularity, an edge in our equations where density and space-time curvature blow up. Real black holes, though, almost certainly spin because the stars and gas that feed them carry angular momentum. A rotating hole is described by the Kerr solution. In that math, the singularity is not a point, but a ring. The rotating space-time also drags nearby space around with it, an effect related to frame dragging. Some versions of the equations allow paths that loop in time or routes that seem to lead elsewhere, but smooth interiors like that are fragile. In realistic situations, small fluctuations in the falling matter may grow into chaos, shredding neat structures and making the inner region turbulent rather than tunnel-like. A charged black hole, called Reisner-Nordström, adds another twist. The equations predict two horizons, an outer one much like the usual point of no return, and an inner one where the roles of space and time can swap in puzzling ways. Between them, motion can behave unlike anything outside. In practice, astrophysical black holes probably shed net charge quickly by attracting opposite charges from their surroundings, so the double horizon layout may be short-lived or never cleanly realized in nature. Even so, the solution reminds us that black hole interiors depend on more than mass alone. Put together, these examples say the inside story is not one size fits all. Two black holes with the same mass could hide different geometries because their pasts differ: how they formed, what they swallowed, whether they spin, how steady or clumpy the infall has been. The puzzle deepens when black holes merge. We have firm evidence for mergers from gravitational waves, the ripples in space-time recorded by observatories like LIGO. Those signals trace the dance, the crash, and the final ring-down as the new hole settles. What they do not yet reveal is the fate of any inner structure. Some scientists think traces of an interior might survive and leave faint patterns in the waves. Others expect a thorough scramble that erases prior details. Future detectors, more sensitive and covering wider bands, may be able to test these ideas and sort subtle echoes from noise. Beyond diversity, black holes point to a startling comparison with the universe itself. There is a quantity called the Schwarzschild radius. For any mass, it is the radius a sphere would need to have to be a black hole. If you add up the mass in the observable universe and compute that radius, you get a number on the order of the universe's size. That raises a quiet question. In a certain mathematical sense, could our universe already fit inside its own black hole threshold? Daily experience pushes back. We do not feel a global collapse. Space is expanding, but a black hole is defined not only by falling matter, it is defined by the shape of space-time. When physicists compare models of an expanding universe with the interior of certain black hole solutions, they find shared features. Inside a black hole, beyond the horizon, a direction that we think of as spatial can act like time. Motion inward becomes as unavoidable as moving into the future. In a growing universe, space stretches in every direction, and the Big Bang acts as a boundary in time. Nothing we observe can come from before it, which behaves a little like a horizon in reverse. Ideas along these lines go back decades. Andrei Sakharov suggested that the Big Bang might be a bounce rather than a beginning from nothing. Later work explored how a black hole's inner region could connect to a new expanding space. In some solutions to Einstein's equations, collapse feeds a bridge to a fresh region, a baby universe, that is hidden from the parent by a horizon. From the outside, the black hole remains small and simple. From the inside, the newborn cosmos grows with its own space and time. Reframing black holes as beginnings instead of endings changes what they mean. If each black hole can seed a new universe, then our own universe might have started inside a black hole that formed in a larger, older cosmos. This picture carries a certain economy. It might help explain why our universe landed on values that let atoms form, stars shine, and life emerge. The balances of energy and pressure that define a black hole could set the initial conditions for the interior universe it spawns. There are cautions. Saying the universe is inside a black hole can mislead if taken too literally. We cannot point to a horizon around the whole cosmos, nor can anyone outside look in. The analogy is about matching the geometry and behavior of space-time, not about watching our universe fall through a surface. Some physicists view the resemblance as a sign of common structure rather than identity. The same deep rules that shape black holes might shape entire universes. Pushing further, Lee Smolin and others have proposed cosmological natural selection. In that view, universes reproduce through black holes. Those with laws that favor star formation make more black holes, and thus more offspring universes. Over many generations, parameters drift toward values that make black holes and, by side effect, make long-lived stars and heavy elements more common. Evidence for these bold ideas is not in hand. We have no direct measurement that shows our universe came from a black hole, and we cannot see beyond our cosmic horizon to check. The case today is theoretical, built from equations and consistency more than from observation. Still, the questions are worth pressing. As we learn more about the early universe, as we test gravity with sharper images of horizons and with clearer gravitational wave records, and as we inch toward a working theory that unites the quantum and the cosmic, we may find that black holes and universes are branches of the same root. In that frame, the voids we feared as endings become engines that carry the rules of space-time forward, passing information and structure into new realms we can only infer from the quiet signals left behind. Those same signals point to the boundaries that ration what can be known, horizons that mark where information stops. The question is whether the horizon of our universe behaves like the event horizon of a black hole. No matter how sharp our telescopes become, there is a built-in limit to sight. This limit is not fog or dust. It comes from the speed of light and from the way space expands. The boundary is called the cosmic horizon. Beyond it, space and galaxies continue, but their light has not had enough time to reach us since the beginning of cosmic time. It is not only far, it is forever out of reach, because the expansion keeps stretching the distance faster than light can close it. In this way, the cosmic horizon acts like a quiet border. We know something lies beyond, yet no signal from there can arrive here. A black hole's event horizon is also a border. It marks the place where escape ends. Matter and light can cross inward, but nothing comes back out. To an outside observer, the interior stays hidden, no matter how clever the experiment. The similarity with the cosmic horizon is striking. Both boundaries set a hard limit on knowledge. Still, they are not the same thing. A black hole horizon is local. It surrounds a single compact object, and its shape depends on the hole's mass and spin. The cosmic horizon is global. It belongs to the universe as a whole and grows or shrinks with cosmic history. Early on, when the universe was young, the horizon was small because there had been little time for light to travel. As time passed, the horizon expanded and more of the sky came into view. With accelerated expansion, some galaxies we can see today will slip out of sight later. They do not vanish. Their light is stretched so much by the growing space between us that it will never reach us again. There is a deeper tie between these horizons. Each one can be assigned a temperature through quantum physics. A black hole emits Hawking radiation, a faint glow from quantum effects near its event horizon. A universe with steady, accelerated expansion carries a related feature called a de Sitter horizon. It too has a tiny temperature connected to the expansion rate. The number is unimaginably cold, but it is not zero. Even empty space far from stars whispers with this thermal trace. If horizons have temperatures, they also have entropy, a measure of hidden information. This means a horizon is not just a line on a diagram, it is a physical part of how the world stores and processes information. Are we then trapped in a black hole-like situation on a cosmic scale? Not exactly. We are not inside a black hole in the ordinary sense. and there is no outer observer to watch us freeze at a surface. But the parallel teaches us how limits arise. The cosmic horizon is a boundary for experience, a frontier past which events cannot affect us. In that sense, it is a real feature of space and time, not just a flaw in our tools. Like the event horizon, it divides what can be known from what cannot, and it shapes the flow of information available to any observer. Horizons are also personal. A person falling into a black hole does not feel a wall at the horizon. They cross it smoothly. The wall exists only for someone watching from far away. The cosmic version is similar. Because of motion and position, each observer has a slightly different horizon, a slightly different slice of the universe. What is real for one observer, what can be measured and influenced, may not be part of reality for another. This idea leads to horizon complementarity. No single observer can hold the whole picture, yet different observers can each have a complete, self-consistent story within their own horizon. Inside a black hole, the infaller and the distant watcher disagree about what happens, and both descriptions can be valid in their own domains. In the cosmos, each of us lives inside a horizon set by our past light cone and by the ongoing expansion. Beyond it are events that, for us, do not occur in any actionable way because they can never send a signal here. From horizons, a second idea emerges. The universe might work like a hologram. In the 1970 seconds, Jacob Bekenstein argued that the information content of a black hole scales with the area of its event horizon, not with the volume inside. Stephen Hawking later showed that black holes radiate and can evaporate. This raised a puzzle. If a black hole disappears, where does the information about what fell in go? Quantum mechanics says information is never truly destroyed. To keep that rule, the information must be stored on or near the horizon and be recoverable in principle from the outgoing radiation, however scrambled. The lesson is that nature may keep its books on surfaces. The holographic principle extends this lesson. Think of a region of space like a cube. Intuition claims the information within should scale with the cube's volume. Holography says the true count scales with its surface area. In other words, a two-dimensional boundary could encode everything about the three-dimensional interior. This is not a trick picture. It is a statement about how the laws of physics might be organized. In the late 1990 seconds, Juan Maldacena found a precise example of this idea in a special kind of universe. A theory with gravity in a higher dimensional bulk turned out to be exactly equivalent to a theory without gravity on the lower dimensional boundary. The two descriptions look different, but carry the same information and make the same predictions. Space and gravity in the bulk can be seen as emerging from quantum data on the edge. Our universe is not of that special type, and it is expanding rather than curled the way that example assumes. Even so, the correspondence proves that a holographic description is possible in principle. It suggests a new way to think about the link between quantum mechanics and gravity. If gravity can emerge from quantum information on a boundary, then space-time itself might be secondary built from patterns of entanglement and information, rather than being a fixed backdrop. In this view, surfaces are where the fundamental bits live, and volumes are what those bits generate. Evidence for surface-based bookkeeping shows up in many places. When physicists estimate the maximum entropy allowed in a region before it collapses into a black hole, the result scales with area, not volume. Calculations in quantum field theory also reveal area laws for entanglement in many settings. Thought experiments about packing information into a box hit the same wall beyond a certain point. Adding more bits forces a horizon to form, and the capacity again grows with area. The pattern is consistent. Nature seems to favor boundaries when counting information. If the universe is holographic, where is the screen that holds the code? It could be tied to the cosmic horizon, the ultimate boundary of what can be observed by any one observer. It could be a mathematical surface at extreme distance, or it could be something we do not yet have language for, a structure that lives outside ordinary space. What would this mean for our daily experience? It would not make chairs less solid or time less real to us. The three-dimensional world would remain the right description for what we do and measure. The claim is deeper. The most fundamental description might live on a surface we cannot touch, while our space, time, and gravity arise from it the way a three-dimensional scene arises from a flat hologram. Seen together, horizons and holography change how we think about limits and about reality. The cosmic horizon teaches that there are regions we can never access, because expansion outruns light. The black hole horizon shows how gravity can hide information and give it a temperature. Horizon complementarity proposes that reality can be observer-based without being inconsistent. The holographic principle adds that information wants to live on surfaces and that space-time might be the large-scale pattern of that information. None of this says our universe is inside a black hole in the usual sense. It says the same logic that shapes black holes may shape the cosmos at large, and the same rules that keep information on an event horizon might also govern the edges of what any observer can ever know. Many details remain open. We still do not know whether the cosmic horizon is the right boundary for a holographic code, how to read such a code if it exists, or how Hawking radiation encodes the full story of what fell into a black hole. What we do know is that limits are telling us something about how space and time organize themselves, about how information is stored, and about why some parts of the universe are forever beyond reach, even as their quiet influence helps define the world within our sight. Those limits naturally point to the next question: what first set the expansion in motion? The Big Bang is our standard opening scene, a moment when space, time, matter, and energy began to expand from an extremely dense, hot state. It sets the timeline of our universe and explains why distant galaxies drift apart and why the oldest light, the cosmic microwave background, fills the sky with a nearly even glow. Yet the picture may not be a beginning from nothing. There is another possibility that sits quietly inside the equations of gravity: a white hole. A white hole is the time-reversed cousin of a black hole. A black hole traps everything that crosses its event horizon. Nothing escapes. A white hole does the opposite in theory. Nothing can fall in, and whatever is inside must come out. It is a fountain rather than a trap. If you take the math for a black hole and flip time's arrow, you get a solution that behaves like a white hole. We have never seen one. We have strong evidence for black holes from orbiting stars, X-rays from hot gas, and gravitational waves from mergers. White holes remain hypothetical. But the equations that allow black holes also allow their mirror images, at least on paper. This mirror opens a curious link to our origin story. The Big Bang looks like an outward burst. A white hole is an outward burst. The link is more than a visual rhyme. A white hole can be imagined as the rebound of material compressed past any ordinary limit. If the Big Bang were a white hole event, the matter and energy of our universe could have been squeezed in a black hole in some older, larger cosmos, then released into a new region of space and time ours. Modern ideas in quantum gravity try to make this precise. General relativity predicts a singularity, an edge in the math, at a black hole's center. Loop quantum gravity proposes that space is built from tiny loops, so there is a smallest scale. In that view, collapse does not end in a true singularity. Quantum pressure rises before infinite density is reached, and the collapse can bounce. On the far side of that bounce, the interior could look like a white hole, pushing matter into a fresh space-time. In this sense, a black hole can act like a seed. The seed does not sprout in the parent universe. It opens into a child universe, hidden behind a horizon. Observers living inside such a child cosmos would not notice the parent. They would see expansion, measure a hot, dense past, and tell a Big Bang story that looks like ours. The origin would be invisible from within, as if a curtain were hanging at time zero. This picture also softens a question about time itself. If time began at our Big Bang, what set it going? If our universe formed from a bounce inside a parent black hole, then time did not start with us. It continued. What we call the beginning would be a transition in a larger flow, not the first tick of a cosmic clock. The white hole idea also gives a path for what happens to matter inside black holes. If nothing escapes, where does it go? Is information lost? The white hole picture says the story is not an ending, but a handoff. Matter and energy are not destroyed. They are repackaged and released into a new arena, preserving the rule that information is never truly erased, only transformed. The cycle would be destruction and creation linked by a bounce. There are serious challenges. We have no direct sighting of a white hole. The conditions to create one may be rare or may never occur in our universe. The laws that govern a transition from a black hole to a new spacetime are not settled. Even so, the idea keeps its seat at the table because it connects to puzzles we already face. One is the horizon problem. The cosmic microwave background is almost the same temperature in every direction, even across regions that could not have exchanged light after the Big Bang. Inflation, the theory that space expanded extremely fast very early on, explains this by stretching a once tiny, uniform patch to cosmic size. A white hole origin could also produce uniformity. Matter and radiation, compressed before the bounce could reach thermal balance, then expand into a new universe already smoothed out. The two ideas are not enemies. They are different routes to the same observed calm. Another principle in the background is cosmic censorship. General relativity seems to prefer that singularities stay hidden behind horizons, shielding the rest of the universe from their extremes. Black hole cores are invisible in this way. The Big Bang looks like a visible singularity, the one case we can see through its relic light. A white hole interpretation fits the rule. The singular behavior would remain hidden in a parent universe, while we witness the gentle side, the expanding aftermath on our side. The holographic principle adds still more context. It proposes that the true accounting of information in a region lives on its boundary, not in its volume. If a new universe grows from a black hole, the change could be framed as a reorganization of information across a horizon. One side looks like a black hole to the parent, the other like a white hole to the child. The matter does not tunnel through in the ordinary sense. Rather, the underlying quantum information is rearranged so that a new spacetime emerges on the far side. There are versions of the idea that stay within our own cosmos. Some models suggest that an ancient black hole, after losing mass through Hawking radiation for an immense time, could transition into a white hole and release what it once swallowed back into this universe. That would not create a new cosmos. It would be a late-time return. Whether nature ever takes this path is unknown. The point is that the equations do not forbid a rebound. All of this leads to a careful question. Could our Big Bang have been the outward face of a white hole in a larger world? If so, Our 1-3+ billion year history would be part of a bigger family tree. Each black hole in a parent universe could seed a child universe. Each child could grow, form stars, and make its own black holes, spawning more branches. In such a picture, black holes are not only endpoints, they are cradles. White holes, while still hypothetical, are the birth side of that cycle. No observation today settles the case. We cannot step outside our horizon to check for a parent, and we cannot look back past the veil of the earliest moments to watch a bounce occur. What we can do is test the pieces we can reach. We can scan the microwave background for subtle patterns. We can measure gravitational waves that tell us how horizons ring and fade. We can sharpen images of black hole shadows and compare them with predictions. We can push toward a theory that unites quantum rules with gravity so that singularity becomes a solved problem rather than a warning label. If the white hole path turns out to be wrong, it will still have pointed us toward better questions about time, information, and the shape of beginnings. If it turns out to be right, our Big Bang will stand as one bright link in a long chain. Either way, the lesson is steady. The universe seems to prefer continuity over abrupt endings, transformation over destruction. Matter and energy cycle through forms. Horizons hide details, but keep the books. And even in the darkest places we know inside black holes, there may be the conditions for a new space to open, a new clock to start, and a new sky to light up with the first glow of creation. Picture a cosmos that does not stretch forever. Far ahead on the timeline, expansion could slow, stall, and turn around. Gravity, tugging on all matter and energy, might regain the lead. Galaxies would edge closer. Stars would burn out and dim. Matter would clump and heat as space itself shrank. The clock could seem to run faster while everything rushed inward. This slow return has a name: the Big Crunch. It is the mirror of the Big Bang, less a burst than a long, deep fold. In such a collapse, densities soar until our familiar laws stop giving good answers. The endpoint looks like a singularity, the kind we expect at a black hole's core. And just as a dying star can make a black hole, the end of an entire universe could set the stage for something new. Some versions place this collapse inside a higher dimensional setting, a larger arena we cannot sense directly. In that wider space, a whole universe curving in on itself would resemble a black hole forming. To observers inside, the same event could look like a new beginning, a fresh expansion, a young sky, and no hint of what came before. One picture, two viewpoints, both drawn from the same geometry. Ideas like this appear across modern theory. Cosmological natural selection proposes that black holes can seed new universes beyond their horizons. Offspring universes might differ slightly. Gravity a bit stronger or weaker, particle masses shifted, a new balance among forces. Over many generations, universes that make more black holes leave more descendants, those that do not fade from the family tree. By this logic, a cosmos rich in long-lived stars and heavy elements would be fertile, because those traits help form black holes. What looks like fine-tuning could be the result of a long history of cosmic trial and error. Loop quantum cosmology takes a different route. It replaces singular endings with bounces. As matter compresses, quantum effects grow and set a limit. Collapse, stalls, then reverses. The end of one cycle becomes the start of the next. Push the idea farther, and every black hole could be a seed for a separate region of space-time. From inside each region, it feels like a clean beginning. From a broader view, the picture branches like a growing tree, with universes budding from the depths of stars and the mergers of horizons. Taken together, these strands sketch a kind of multiverse, many universes, each with its own history, each able to produce more. Where would such growth occur? If a collapsing universe acts like a black hole in higher dimensions, the outside would be that bigger space. What does it mean for one universe to sit inside another? Our math does not yet settle the question. The key point is that the same equations can describe both views, and the change in viewpoint alters what counts as beginning or end. Could we tell whether our world lies inside a black hole? From within, we would never see an edge. A horizon, by design, sits beyond reach. Space would bend so strongly that light and everything else would be drawn inward forever. To us, the universe would look endless in all directions, even if it had a limit we could not touch. In practice, that already matches how the sky behaves. We do not find a wall. We see galaxies grow fainter and redder as they recede, their light stretched until it slips beyond our instruments. Some researchers have asked whether this deep redshift could be a sign of strong curvature tied to a surrounding black hole. The idea is debated, but it shows where clues might hide. Math adds sharper threads. The equations that track our universe's expansion share forms with those that describe the interior of a rotating black hole. In both settings, space is not static, and clocks do not tick at the same rate everywhere. Distances warp. Rates of time change with position. The parallels are close enough that some suspect a shared cause, rather than a coincidence. Conditions that birth a black hole in a larger world might set the shape and growth of a cosmos like ours. Geometry on the larger scales could offer another hint. If the universe is closed, curving back on itself like the surface of a sphere, then it is finite, without edges. A finite interior wrapped in higher dimensional space would fit the way a black hole's inside is bounded yet looks unbounded to those within. You could travel forever and never hit a wall, while an outside view would see a contained volume. Information and entropy point the same way. For black holes, the maximum information scales with the area of the horizon, not the volume inside. This is the seed of the holographic idea. Nature may keep its records on surfaces. If our universe follows a similar rule, reality could be holographic at large scales too. Everything we can observe would be encoded on a distant boundary we cannot reach, setting a strict information budget for our entire visible world. The oldest light in the sky, the cosmic microwave background, could hold fingerprints of such an origin. This afterglow is smooth but not perfect. Its tiny variations and slight alignments have sparked long debates. If our cosmos grew from a violent, perhaps rotating collapse in a parent system, the turbulence and spin might leave subtle imprints in that ancient light. These signals would be faint and tangled with noise, yet they are exactly the sort of patterns we can map and test. Spin matters for another reason. Most black holes rotate because the matter that formed them carried angular momentum. If a rotating hole seeded our universe, a trace of that spin could influence how structure formed, setting preferred directions or small twists in the motions of galaxies on the widest scales. Any such rotation would have to be tiny. Surveys so far do not show a clear global spin. Still, improved data keep the door open to more sensitive checks. Dark energy is a further puzzle wrapped into this frame. We use that name for the cause of the accelerated expansion we observe. In a black hole-like interior, some of that push might come from geometry itself, rather than a new substance. The acceleration could be a built-in feature of the curved region we inhabit. This is a working picture, not a finished model, but it shows how ideas about horizons and interiors can recast old questions. Even the finest grain of space-time could weigh in. If space and time are not perfectly smooth but built from tiny units, then any region has a hard cap on how much information it can hold. Black holes already teach that lesson. If quantum gravity confirms a universal limit of this kind, it would support the view that our universe has boundaries in the informational sense, the way a black hole does. Ultra-high energy cosmic rays might also whisper about hidden structure. If the highest energy particles behave oddly or cut off in unexpected ways, extra dimensions or boundary effects could be involved, hinting that our visible world sits inside a larger shape. No single experiment can settle the question soon. We cannot travel to an outside and look back. What we can do is compare patterns, how light stretches with distance, how structures align across the sky, how the background glows, how horizons ring when black holes merge and settle. If those patterns match the signatures expected for an interior shaped by black hole physics, our picture of reality will change. Space, time, and the meaning of beginning would be redrawn with new lines that still respect what our instruments see. In this view, the universe is both familiar and strange. It looks limitless from within, yet it could be held by an unseen boundary. Galaxies drift apart as space flows, yet information follows surface rules. Dark energy becomes a sign of curvature rather than a separate force. Time itself may run with a bias set by the larger geometry that holds us, felt only in the widest averages and the oldest light. And even in the darkest places we know inside black holes, there may be the conditions for a new space to open, a new clock to start, and a new sky to light up with the first glow of creation. Physicists have spent recent decades asking a careful question: what happens to information when a black hole fades away through evaporation? The issue is not just the appetite of the hole, it is the slow leak of energy called Hawking radiation, drop by drop, and whether the fine details of what fell in are gone forever. To probe this, researchers use ideas from quantum information and quantum entanglement. Entanglement is a link between particles that makes their properties line up even when they are far apart. Measure one, and you learn something about the other, as if a hidden thread ties them together. Out of this work came the Page curve, named for Don Page. Imagine a graph that tracks how much information seems locked inside a black hole as it radiates. Early on, the curve falls the wrong way. The outgoing radiation looks random, so it appears that information is sinking out of reach. Then, after enough time has passed, the Page time, the curve bends upward. Patterns begin to show up in the radiation. Bit by bit, the information that looked lost starts to come back out, scrambled but not destroyed. By the end of evaporation, the curve says the book is balanced. The universe keeps memory. Nothing is erased. It is only delayed and mixed. That picture makes a black hole look like an extreme quantum device. It accepts data, hides it behind the horizon, stirs it with unbelievable complexity, and later releases it in a code we barely know how to read. To test this idea, theorists build simplified toy models that capture the key pieces without the full mess of the real world. Some of these models reproduce the Page curve. Others show how the entanglement between the hole and its radiation could carry information outward in a lawful way. These results do not settle the case, but they give confidence that the broad story may be right. Not everyone agrees on the path. A sharp alternative is the firewall. In standard general relativity, the equivalence principle says that a freely falling observer feels no gravity. Cross the horizon of a huge black hole, and, in that view, nothing special happens at first. The drama lies far inside, near the singularity. A firewall overturns that story. It says the horizon is a sheet of intense energy. Touch it, and you burn at once. Calm crossing is replaced by instant destruction. Why would anyone accept such a harsh fix? Quantum mechanics carries a rule called monogamy of entanglement. In plain words, a single quantum system cannot be perfectly entangled with two different partners at the same time. For Hawking radiation to carry information away, new radiation leaving the hole must be entangled with radiation that left earlier. If that is true, the same new radiation cannot also be perfectly entangled with the stuff still inside. Something has to give. In 2012, Ahmed Al-Mehri, Donald Marolf, Joseph Polchinski, and James Sully argued that the price is a broken horizon, a firewall that saves quantum rules by sacrificing smooth spacetime at the edge. That claim set off a fierce debate. A firewall seems to punch a hole in the equivalence principle, a pillar of Einstein's theory. If spacetime tears at the horizon, relativity would lose its quiet grace exactly where gravity is strongest. Many physicists see this as too high a cost and search for gentler answers. Perhaps information escapes in a more subtle way we have not yet mapped. Perhaps our usual view of entanglement bends when gravity is included. The goal is to keep both. Unitarity, from quantum mechanics, the rule that probabilities sum to 1 and information is preserved, and the smooth crossing from relativity. A daring path shifts the ground under both sides. It says spacetime is not fundamental. Instead, geometry emerges from patterns of entanglement. In that case, the firewall paradox might rest on a wrong starting point. The inside and outside of a black hole could be connected more deeply than we guessed. The slogan, ER equals EPR, captures one way this might work. ER refers to Einstein-Rosen bridges, or wormholes. EPR refers to quantum entanglement as discussed by Einstein, Podolsky, and Rosen. ER equals EPR suggests that entangled systems are joined by tiny, non-traversable wormholes. No traveler passes through, but the connection is real in the math. Through these hidden links, the interior can remain tied to the radiation. Information would not need a firewall to escape. It would ride out on lawful correlations already woven into spacetime. If something like ER equals EPR is right, the horizon stays smooth. The page curve is respected. Quantum rules and relativity share the win, though in a way that asks us to trade old pictures for new ones. The hole does not break the laws. It reveals where those laws come from and how they fit together. This choice between firewalls and wormhole-like links is more than a technical argument. It cuts to the meaning of continuity in nature. Does reality break at sharp edges? Or does it hold together through hidden structure? Do we need to replace parts of general relativity? Or can we rebuild space-time from quantum information so that the old principles emerge as excellent approximations? Black holes push the questions to their limits because they combine extreme curvature with quantum effects in one place. No single calculation will close the book tomorrow, yet progress is steady. Toy models now recover the page curve using techniques from quantum information theory. New gravitational wave events let us test how horizons ring and settle. Ever sharper images of black hole shadows probe the geometry just outside the edge. Each result narrows the space of possible answers and points to the next calculation to try. However the paradox resolves, the lesson is the same. Black holes are not blank endings. They are working laboratories. They show that space and time are flexible, that information and geometry are connected, and that the largest and smallest scales must be told in one story. Whether horizons are perfectly soft or hide new microstructure, whether information leaves as fine-grained radiation patterns or through deeper links in space-time. The hunt refines our tools and our sense of what counts as an explanation. The quiet glow of evaporation, the tangled web of entanglement, and the calm or violent behavior at the edge all serve one purpose: to bring quantum mechanics and gravity into a single, clear frame. Black holes are among the strangest objects in the sky. They are so dense that once light gets too close, it cannot escape. The boundary that marks this point of no return is the event horizon. Anything that crosses it, light, matter, energy, does not come back out. Yet black holes are not silent or eternal. At their edges there is a faint leak, a thin glow called Hawking radiation. It was proposed in the 1970 seconds and says that even a perfect darkness can whisper. The idea begins with empty space, which is not truly empty. Quantum rules allow tiny pairs of particles to flicker into being for a moment and then cancel out. These are virtual particles. Near a horizon, one partner can fall inward while the other escapes. The escapee becomes a real particle. To pay for that particle, the black hole gives up a sliver of its own energy. Each escape shrinks the hole by an almost unthinkable amount. The process is slow beyond everyday sense. A black hole with the mass of a star would take far longer than the age of the universe to fade away. To us, it looks permanent. Given enough cosmic time, though, the leak wins and the hole ends in a final, tiny burst. When Hawking introduced this radiation, he treated it like heat from a fire, featureless and random, that led straight into the information paradox. Physics says information is never truly destroyed. It can be scrambled or hidden, but not erased. If the outgoing glow is pure noise, then the details of what fell in, down to the finest arrangement of particles, would be lost. Over time, the view shifted. Many researchers now suspect the radiation is not completely random. It may carry subtle patterns, a code that, in principle, records what went in. If so, black holes work less like shredders and more like extreme mixers. They take a clean message, stir it beyond recognition, and release it in a form that looks simple until you measure it with painful precision. Detecting Hawking radiation directly is close to impossible with today's tools. The glow is much fainter than the background of the universe. So physicists also listen in another way, by watching how space-time itself vibrates when black holes collide. When two holes spiral together, they send ripples through space-time called gravitational waves. These waves do not scatter off dust or gas. They carry a clean record of the motion that made them. The story of a merger has three broad phases that flow into one another. First comes a long, tightening spiral as the pair circle and draw closer. Then comes the brief crash when the horizons meet and fuse. Finally, the new, larger black hole rings as it settles. That ringing phase is called the ring down. Think of tapping a bell and hearing a tone that fades. A black hole has its own set of natural tones, quasi-normal modes. Their exact mix depends on the hole's mass and spin. By measuring them, we can read basic properties from a source many billions of light years away. We have already heard several such events. Observatories like LIGO and Virgo have recorded short stretches of data that reveal the masses and spins of merging holes with surprising accuracy. As instruments improve, the goal is to resolve finer structure. Small shifts in the ring down could hint at new physics, tiny departures from the standard picture, subtle echoes, or narrow features that are hard to see now. In those details may lie clues not only to the shape outside a horizon, but also to the rules that control the edge itself. This raises a puzzle. If no signal comes out from inside the event horizon, how could Ringdown tell us anything about an interior? One answer is that the inside may be written on the outside. Studies of black hole thermodynamics and string theory suggest that the number of possible internal states grows with the area of the horizon, not the volume within. It is as if the surface stores the data. In that case, everything that has ever fallen in would leave a record on the boundary. The way the hole radiates, rings, and tugs on nearby matter could all be shaped by that hidden bookkeeping. Decoding those patterns is like reading raised letters by touch. You never see the page, but the surface carries the message. For years, black holes were said to have no hair. The phrase means that a stationary black hole is fully described by just 3 numbers: mass, spin, and electric charge. 2 holes with the same 3 values are indistinguishable, no matter how they formed. Recent ideas challenge this strict view. The surface might have soft hair, very delicate features tied to the hole's history. These would not be obvious. They would appear as tiny shifts in radiation, as barely there twists in the ring-down tones, or as slight imprints in how a hole responds to what orbits near it. If such hair exists, black holes are not forgetful. They are careful archivists with an odd filing system. The prospect of reading these archives depends on better measurements and better theory. On the measurement side, future gravitational wave detectors will be more sensitive and cover wider bands. Longer observations will catch in spirals earlier and track more cycles, sharpening our estimates of mass and spin and revealing weaker modes in the ring-down. On the theory side, cleaner predictions for how quasi-normal modes behave in more realistic settings, fast spin, small environmental effects, possible quantum corrections will guide what to look for in noisy data. The 2 sides must grow together. Data suggest where the models bend. Models tell us which signatures are worth chasing. Hawking radiation remains a crucial part of the picture, even if we cannot measure it directly. It sets the long-term fate of isolated black holes and frames the information problem. If the radiation encodes the story of what fell in, then the universe keeps faith with unitarity, the rule that quantum evolution preserves information. If, instead, the glow remains truly random, we face a break in the logic that connects past to future. The weight of recent work favors the first path. Information is preserved, though in forms that are hard to recognize and harder to recover. Gravitational waves offer a complementary test of the horizon's character. If the edge is perfectly smooth, ring-down should match the tones predicted by general relativity to high precision. If there is new microstructure at the boundary, tiny departures might appear. These would not be fireworks. They would be slight delays or faint echoes, near undetectable extra notes in the dying tone. Distinguishing such signals from instrument noise and from ordinary astrophysical clutter is a hard task. It demands many events, careful statistics, and agreement across different detectors. All of this circles back to a simple point. Black holes are not blank. They leak energy, they ring with specific tones, and they may carry a record of their past on their surfaces. Each of these facts turns a black hole into a kind of instrument. The Hawking glow, though dim, tells us about quantum fields in curved spacetime. The waveforms from mergers tell us about strong gravity and motion. The possibility of hair hints that information and geometry are bound together more tightly than we once thought. Step by step, these tools change how we study the darkest places. Instead of looking for light, we listen for shape. Instead of expecting pure silence, we expect structure. With more sensitive ears and cleaner theory, the notes we hear from ringing horizons will do more than confirm equations. They will test the link between quantum information and space-time. The path is long, but the method is clear. Follow the faint glow, trace the ripples, and let the data decide how black holes keep their stories. Since 2015, gravitational wave observatories have recorded dozens of black hole mergers. These signals confirm that black holes are common and that their behavior largely fits general relativity. Even so, we are still early. The signals are short and often noisy. The ring down, the part that best probes the edge of the horizon, lasts a fraction of a second, and by the time the waves reach Earth, they are faint after crossing millions or billions of light years. Detector technology is climbing fast. The current ground-based instruments, LIGO and Virgo, are the first step. The planned Einstein telescope aims to reach far greater sensitivity. In space, the LISA mission will fly 3 satellites in a triangle, separated by millions of kilometers, listening for low-pitch waves from supermassive black holes in galactic cores. Those signals can last hours or days, giving time to resolve fine structure in the ring down and to compare what we measure against different theories. In such detail, new physics might show up. Quantum effects, usually buried on tiny scales, could leave small shifts in the tones a black hole plays as it settles. Alternative gravity models might predict slightly different mode patterns. If so, gravitational waves become not only a way to observe the sky, but also a way to test the foundations of physics. Some bold ideas even question whether real black holes have perfect event horizons. Just outside the edge, there could be extra structure, a fuzzball of tangled strings in one proposal, or another kind of exotic matter. In those cases, the ring down may not fade smoothly. It could include faint echoes, delayed repetitions of the main tone, like hearing your voice bounce in a canyon. Searches for echoes in present data have given mixed results, some hints, many counter-arguments, but the possibility keeps the effort active because any confirmed echo would point to new structure at the horizon. Even without echoes, waveforms hold more than a simple mass and spin story. A merger changes the gravitational field in a precise way, and those changes ripple outward. We cannot see inside the horizon, but the surface behavior carries information. It is like reading a drum. You do not see the inside, yet the vibration tells you how the skin is tensioned and whether something is rattling beneath. Tiny delays and phase shifts in the waves encode how space-time is curved near the edge. With today's tools, we can tell when a merger happens and estimate masses and spins. With more events, better sensitivity, and sharper models, we can build a catalog of voices. Each collision would be a distinct performance whose overtones hint at how close the real horizon is to the ideal one. A second thread asks whether some objects we call black holes could actually be wormholes. A wormhole is a shortcut through space-time. The picture is simple. Draw 2 far-apart points on a sheet of paper. Fold the paper so the points meet. A small hole now connects them directly. In general relativity, wormholes are allowed by the equations, but they tend to pinch off too quickly to use. Later work showed that negative energy, an exotic form that pushes outward, could prop a throat open in theory. Quantum physics does allow brief negative energy effects, so the idea stays on the table, though no known bulk material behaves that way. From the outside, a wormhole could look much like a black hole. Both bend light strongly, both cast a dark shadow against glowing gas. The difference lies in the interior. Falling into a black hole ends in crushing gravity. Falling into a traversable wormhole, if one exists, would bring you out elsewhere, another place in our galaxy, another galaxy, or in some proposals, another universe with its own space-time. How would we tell the two apart? Only indirectly. A wormhole might leave unusual signatures, flashes or jets with odd timing, gravitational tugs that imply a partner mass beyond the throat, or repeating ring-down features as vibrations bounce within the tunnel. These signs would be faint and easy to confuse with noise or ordinary astrophysics. Simulations help by predicting what patterns to seek. Observers then compare those patterns with data, looking for small mismatches with the black hole picture. An even tighter link connects wormholes to quantum entanglement. Entangled systems share correlated outcomes no matter how far apart they are. The idea, nicknamed ER equals EPR, proposes that entangled pairs are connected by tiny, non-traversable wormholes, Einstein-Rosen bridges. No traveler goes through them, but the connection is real in the math. If that view is right, space-time geometry is woven from entanglement itself. In that case, the smoothness of a horizon would reflect how quantum information is arranged, and the patterns in gravitational waves would be reading that arrangement at large scale. Could anyone ever travel through a wormhole? The honest answer is that we do not know. Many would be far smaller than atoms. Larger ones, if they exist, might be unstable. Even a stable throat would be dangerous. Tidal forces, radiation, and navigation problems would be extreme. Proving one exists would not start with travel anyway. It would start with careful, repeated measurements that pick out features ordinary black holes cannot mimic, and with cross-checks from different observatories and wavelengths. Direct images cannot resolve the interior. The famous ring around the black hole in Messier 87 shows light from hot gas curved by gravity. It does not reveal what lies inside. That is why the indirect pathwave patterns, timing, tiny spectral shifts matters so much. Each improvement in sensitivity and theory narrows the gap between what we can infer and what we want to know. As we stack up more events and compare them with precise models, the voices of these compact objects will outline the physics at their edges and tell us whether the simple horizon is enough or whether extra structure is needed. Falling into a black hole sounds like a straight road to destruction. For many black holes, that picture holds. Near a small, stellar mass hole, gravity changes sharply over short distances. The pull on your feet would be far stronger than on your head. These tidal forces stretch and squeeze at once, turning any object into a long, thin strand spaghettification. It would happen fast, and it would happen well outside the event horizon, long before you reach the point of no return. A supermassive black hole tells a different story. These giants weigh millions or billions of suns. Their gravity is stronger overall, yet the gradient at the horizon is gentler. The difference in pull between head and feet is small there, so you could drift across the horizon with no jolt. There is no glowing line, no click or snap, just an ordinary moment that is not ordinary at all. Past that boundary, no signal you send can return. The last chance to speak to the outside would be just before crossing. After that, you are cut off, even though, to you, time flows in its usual way. From a safe distance, the hole would look like a perfectly dark circle wrapped by a bright ring. Hot gas in a fast disk makes the ring. As you fall, light from stars behind the hole bends around it, smearing into arcs. The sky warps into a lens, shapes twist. Familiar patterns break. Time plays tricks too. For you, seconds remain seconds. For your view of the universe, distant clocks appear to speed up. Light shifts to deeper red and fades. The wider cosmos compresses into a dimming glow. The horizon itself is not a surface, it is a limit. Outside, observers would see your image slow and redden as it approaches that limit, fading toward darkness as if you were stuck. You, however, would continue inward without drama. What waits beyond depends on physics we do not yet have. In classical general relativity, the center is a singularity, a place where curvature grows without bound and every path ends. Inside the horizon, moving inward is as unavoidable as moving into the future. Some ideas from quantum theory soften that end. Instead of a perfect point, the core could be spread out by quantum effects. In that case, the journey might be longer and stranger. Distances might lose clear meaning. Direction might not behave the way it does outside. You could drift through curved pockets of space-time before meeting whatever final state nature allows. The result may still be destruction, but the path there could be complex rather than instantaneous. The flow of time near a horizon also opens a curious possibility. Because clocks run so slowly deep in a gravity well, a falling observer might watch the outside universe rush ahead. In minutes of personal time, the sky could play a fast movie of galaxies drifting apart, stars aging, and light stretching to invisibility. It would not change your fate, but it would change what you could witness on the way. Then the story takes an even more unusual turn. Negative energy. In quantum field theory, the vacuum is not empty. It flickers. Under special conditions, those flickers can produce regions where the measured energy is lower than normal, effectively negative. Negative energy does not act like ordinary matter. It pushes where normal gravity pulls. In theory, a field of negative energy could soften tidal forces, like a cushion around a traveler. Wrapped in such a field, the brutal stretching could be reduced for a time, and the local pull might be eased. Physicists call any substance or field with these properties exotic matter. It does not mean mysterious goo. It means a state with negative energy density or negative pressure relative to the vacuum. A real, measured example on tiny scales is the Casimir effect. Place two very thin metal plates extremely close together in a vacuum. Quantum fluctuations are restricted between them, lowering the energy there compared with the outside. The plates feel a small force that pushes them together. Mathematically, the gap behaves as if it holds a bit of negative energy. It is not a shield you can step behind. It is a delicate effect that shows up only under careful lab conditions, but it proves the vacuum can be stranger than simple emptiness. Could negative energy ever help a person or a probe near a black hole? With what we know today, no. We do not know how to create or maintain large, steady regions of negative energy. The Casimir effect works over microscopic distances and flickers with changes in setup. Scaling that to kilometers and keeping it stable would require control far beyond current technology. Even if you could produce enough, many calculations suggest quantum fluctuations would destabilize any shield, collapsing it before it could help. Because a direct shield seems out of reach, some proposals use negative energy to reshape space instead of fighting gravity head-on. That is the logic behind ideas like traversable wormholes and warp drives. Bend the road so the hazard is no longer on your path. In general relativity, though, stable versions of those structures also demand sustained negative energy in large amounts, and once again, quantum effects likely shut the door quickly by making the geometry unstable. Nature seems to build in safeguards against easy shortcuts. There may still be small roles for negative energy in nature. Short-lived pockets could appear near violent places, close to horizons, in intense particle showers, or in other extreme environments. If they do, they might tweak processes for an instant. Tiny nudges to the horizon's behavior, minute contributions to Hawking radiation, small shifts that vanish as quickly as they form. Such blips would be hard to see, but they keep the topic alive as a target for careful theory and creative experiments. Put together, the picture of a fall into a black hole is layered. Small holes tear and crush fast. Supermassive holes can allow quiet crossing, followed by a drawn-out inward drift. The outside sky warps and reddens. Your own clock remains steady. Classical physics points to a singular end. Quantum ideas hint at a more structured core. Negative energy exists in principle and in tiny laboratory effects, yet cannot be harnessed to save a traveler or open easy tunnels with anything like today's tools. The edge of what we know sits just past the horizon, and the path forward is to keep pairing precise thought with precise measurement as we map how space and time behave where they are most severely tested. Picture a civilization far beyond us, with tools that can shape quantum fields as easily as we tune radios. In theory, such beings might capture and control negative energy. With that mastery, they could wrap a ship in a protective field that cancels the worst tidal forces near a horizon. An explorer might slip across the edge of a supermassive black hole as calmly as a diver enters the sea, not torn into threads, but carried inward under careful guidance. Inside, negative energy could be more than a shield. It could be a steering fin. In a region where space-time twists into strange shapes, a controlled field might make tiny course corrections, nudging a path toward a long-lived pocket, toward the throat of a wormhole, or toward an exit that opens somewhere else. In that picture, a fall would not mean permanent trap. It would be a route. This remains thought, not engineering. No one has built a generator for sustained negative energy, or an exotic matter shell. Nature may even forbid such fields at usable scales. Deep consistency rules could block the very tricks that would cause paradoxes. Still, posing the question has value. It forces us to test the edges of gravity and quantum theory, and to ask what the vacuum itself can do. A few delicate lab effects, like the Casimir setup with metal plates, hint that empty space can carry negative energy in tiny flickering amounts. That whisper keeps the topic alive, while the machinery to scale it lies far beyond our reach. A second path to the interior story comes from string theory. Here, the basic units of nature are not point-like particles, but ultra-teeny strings that vibrate. Different patterns of vibration appear as the particles we know. Photons, electrons, quarks. The image is simple. Change the note, change the particle. Strings also invite extra, hidden dimensions that curl up too small to see, and higher dimensional cousins called branes, membrane-like objects that can carry fields and, in some versions, host entire universes. This view reshapes what inside a black hole could mean. In ordinary relativity, everything collapses to a singularity, a point where density and curvature blow up and the math fails. In one string-based picture, the fuzzball proposal, there is no smooth interior and no point-like core. The mass is stored in a tangle of strings and branes packed near the would-be horizon. Space does not continue inward, the way classical geometry suggests. Cross the surface, and you hit the tangle's edge. The whole is a dense, complicated knot of microstates, rather than an empty well. The object remains deadly because gravity is extreme, yet the classical singularity is replaced by a many-string structure. Strings add another strong idea: holography. Calculations show that the number of possible black hole states scales with the area of the horizon, not its volume. That suggests the surface can encode the interior. The add-CFT correspondence makes this sharp in special spacetimes. A full gravity theory in a higher dimensional bulk can be exactly equivalent to a quantum field theory without gravity on a lower dimensional boundary. Two different languages, one underlying story. Push this further, and even spacetime might emerge from patterns of quantum entanglement, the deep correlations that tie systems together. In such a world, geometry is built from information. A black hole's inside would be a structure of connections, and a singularity would mark the breakdown of a coarse description rather than a literal end of space. Strings could also offer a fresh angle on Hawking radiation. Instead of particles popping from the vacuum near the horizon, string vibrations might leak energy outward in specific ways, giving a microscopic account of the glow. None of this is proven. The math is powerful, but hard to test. The scale's impossibly small. Yet the framework provides a consistent picture in which information is stored and the worst infinities are avoided by replacing the point-like idea with extended, vibrating objects. A different route tries to quantize gravity without strings. Loop quantum gravity, LQG, proposes that space is not smooth, but woven from tiny loops. Think of cloth. From far away it looks continuous, but under magnification it is threads. In LQG, areas and volumes come in discrete units. There is a smallest scale, no infinite subdivision. When collapse drives matter inward, the weave resists being squeezed past that limit. The threads of space push back, like a spring that stiffens as it is compressed. That pushback changes the endgame. Instead of a singularity, the core reaches a maximum density, then rebounds. The collapse becomes a bounce. Inside the horizon, space-time can expand again into a new region cut off from the outside. In some models, the expansion takes the form of a baby universe. The mechanism does not need exotic matter. It follows from quantizing geometry itself. Where pure relativity predicts a dead end, loops open a channel. The contrast with fuzzballs is sharp. In the fuzzball view from string theory, there is no classical interior and no smooth path through the horizon. All microstructure sits near the surface. In the loop view, there is an interior with a quantum-supported core, and the story continues past the point where classical equations fail. Both aim to cure the same disease singularities and lost information, but they prescribe different medicines based on different assumptions. Both predict that the simple classical picture breaks down at extreme density. Both keep faith with the idea that nature avoids literal infinities. These approaches also touch the same themes from different angles. Holography says that horizons count states by area. Fuzzballs show how microstates could populate that count. Loop gravity replaces smooth geometry with quanta of area and volume. Bounces show how those quanta resist infinite squeeze. If space-time emerges from information, as many suspect, both programs are trying to write a cleaner dictionary between the bits and the bends. None of this changes what a black hole looks like from afar. A supermassive object still casts a dark shadow against hot gas. Mergers still ring space-time with quasi-normal tones. The difference lies at the edge and below. How horizons store data, how evaporation encodes a past, whether an interior continues smoothly, and how collapse ends. As theory sharpens and observations improve from gravitational wave spectrograms to horizon-scale images, these models will rise or fall on the details they predict. For now, they sketch a workable way past singularities and turn a black hole's center from a blank into a structure that physics can describe. One striking split between the fuzzball view and the bounce view is how they treat time. In a fuzzball, the story ends at the surface. There is no smooth interior, so there is no after to speak of. In a loop gravity bounce, time keeps going. Collapse reaches a quantum limit. Pressure from the grain of space pushes back, and the future continues as expansion on the inside, possibly as a new cosmos with its own matter, light, and history. That difference feeds into the information paradox. Hawking's evaporation makes black holes fade through a faint glow. At first pass, that glow looked random, as if details of what fell in were destroyed. Fuzzballs answer by storing information in the tangled microstructure near the surface and letting it leak out slowly in the radiation. Bounces tell another story. The information is preserved, but it passes through to the newborn interior and is lost to us behind a permanent quantum curtain. Either way, the aim is the same, save quantum rules without breaking gravity. If our universe began as the inside of such a bounce, we might hope for traces. The cosmic microwave background, the afterglow of the early universe, could hold tiny circles or alignments that hint at a prehistory. None are confirmed, but the sky is mapped with growing care. The bounce picture also revises the endgame of evaporation. Instead of fading into nothing after eons, a hole that reaches the quantum regime could transform quickly. To an outside observer, the object might blink out with a short burst, the last handshake between two regions of space-time, or the moment an interior truly takes off on its own. Some versions even allow faint mathematical links between the inside and the outside, not as open doors, but as subtle ties in the equations. If such ties exist, they would not carry messages in any ordinary sense, yet they suggest that cut off may not mean unrelated. Ideas like these drive new models and new tests, even as they stay just beyond present experiments. Time near and inside a horizon raises deeper questions. Relativity already shows that strong gravity bends time. For a falling observer, outside clocks can seem to race. In minutes of personal time, the wider universe could age by millions or billions of years. In the block universe picture, the full history of space-time exists at once, like a book whose pages are all present, even if we read them in order. Inside a classical black hole, geometry forces every path toward an unavoidable future point, what looks like fate written into the shape of space-time. That picture pulls on ideas about choice and free will. Quantum mechanics complicates it, because quantum systems do not follow single tracks. A full quantum theory of gravity may yet soften the supposed endpoint, reroute paths, or replace the singular moment entirely. White holes, the time-reverse cousins of black holes, add another twist. If certain collapses connect a white hole like outflows, an ending from our view could be a beginning from another. In that loop, collapse becomes expansion, and a dead end becomes a passage. Linked this way, black holes and white holes would mark a cycle of in and out, a rhythm of compression and release that knits regions or universes together. The larger thought is unsettling but simple to frame. Perhaps we already live inside such an interior. We do not notice a wall because the horizon, if it exists, is far beyond what we can ever reach. Imagine standing inside a vast balloon. From within, space looks open and flat, even though you are enclosed by a distant skin. Our universe could be like that, an interior where space itself expands, not into something else, but within itself. Galaxies drift apart as the fabric stretches. The cosmic horizon is not a surface we can fly to. It is a bound on what can ever send us a signal. In that sense, it acts like a quiet, unreachable edge. What makes the idea feel more natural is how a supermassive black hole behaves near its horizon. The larger the hole, the gentler the local tides at the edge. A traveler can cross without feeling a sharp line. If a whole universe were the inside of an enormous collapse, its curvature could be so mild on local scales that everyday space seems ordinary. Mathematically, certain interiors do look like entire expanding universes with familiar physics. That resemblance helps explain why the sky is uniform in every direction and why there is no observable trace of before the Big Bang. If the Big Bang was the onset of expansion inside a bubble, then outside is not part of our world line at all. Baby universes push the idea further. A growing interior can stretch so fast that it pinches off from its parent, sealing the throat behind it. Once detached, it follows its own time and writes its own laws within the range that physics allows. If inflation inside is strong enough, the new region becomes causally separate. If not, it collapses before it matures. We could be such a child world, already cut loose long ago, with no handle left to grip the place we came from. The same logic invites a provocative question. Are new universes budding now inside black holes in the galaxies we observe? If so, each horizon hides its own sky, with its own clocks and chemistry, and perhaps its own questions. From our side, we would never see them. From their side, they would never see us. Yet both would be parts of a larger, branching structure built by the same rules. Quantum tunneling adds a final thread to the picture. In quantum physics, a particle can sometimes show up on the far side of a barrier without crossing in the classical way. The event horizon is a causal barrier, not a wall of matter, but quantum fields live right up against it. If tunneling is possible in that environment, the boundary is not absolutely mute. Particles that should be trapped could, on rare terms, reappear outside. Virtual pairs that flicker near the edge could use the same rules to slip in or out. This line of thought is one way to view Hawking radiation, and one reason to think the interior and the exterior remain tied by lawful correlations rather than sealed apart. The chamber is not open in the classical sense, yet at the quantum level it still shares information through the fine print of the vacuum itself. Across these ideas, the fuzzball's surface memory, the loop bouncer's new beginning, white hole links, baby universes, and tunneling the theme is consistent. Extremes of gravity do not have to end in a blank. They can expose where our current theories stop and where a deeper picture must take over, keeping time, information, and geometry in the story without letting any of them break. Some physicists push the picture further and imagine an interior with layers, like an onion. Each layer would be a different quantum state, its own density, its own energy, its own microgeometry of space and time. Classically, those layers would be sealed off by gravity. Quantum rules add a loophole. Because particles behave like waves, they can sometimes slip through barriers in a process called tunneling. In that view, bits of matter, light, or even raw information could hop from one layer to the next, moving across regions that ordinary motion can never cross. The result is not a single room behind the horizon, but a maze of quantum zones, some long-lived, some flickering, all hidden from outside sight. To see why that is even thinkable, recall what a barrier means in quantum mechanics. In daily life, a barrier is a wall. In quantum theory, a barrier is any place where the energy rules, say, not allowed. Waves are not so easily stopped. They seep a little way into forbidden regions, and if conditions are just right, thin barrier, tuned energy, the wave appears on the other side. Inside a black hole, space-time itself is twisted, so paths that would be open in flat space can be closed. Tunneling offers sideways routes through that twisted geometry. A particle could vanish from one pocket and reappear in another, opening hidden connections within the interior. This leads to the idea of hidden interiors. A straightforward fall would still carry you inward, but quantum routes might fork that journey in ways the classical picture never shows. Near the places a classical singularity would sit, the interior could branch into pockets that hold energy, record information, or seed entirely new regions. They would not be visible from outside, yet they would belong to the black hole's internal architecture. String theory and loop quantum gravity give language for such structures. Space-time becomes foamy and restless at tiny scales, full of fluctuations. In such a medium, tunneling stops being rare. It becomes part of the way geometry itself evolves. Then comes the information question. If particles move between layers by tunneling, where do their details go? The old paradox said a black hole destroys information. Here, the answer is gentler. The information can survive, encoded in the pattern of layers and the paths between them. It may never reach the wider universe in a readable way, but it need not be erased. The inside becomes a quantum labyrinth, not a simple chute to nowhere. Push the thought one step farther, and tunneling could also explain births, not just internal motion. Classical collapse points to a singularity. Quantum rules allow a different endgame. The collapsing core could tunnel into a fresh region of space-time and begin to expand. That new region could inflate into a baby universe, causally separate from us but born from the collapse. Our own cosmos could have started that way, and every black hole could be a possible gate to another, starting a branching family tree of universes. The role of observation complicates the picture again. In quantum theory, the act of measuring does not just reveal, it selects among possibilities. Until then, a system is described by a spread of options, a superposition. Apply that logic to a black hole interior and you get a bold claim. Before anything is observed inside, the interior might exist as a cloud of options, geometries flat or curved, regions connected or split. A conscious traveler is not magic. Observation here simply means interactions that fix outcomes, but those interactions can pin down which interior is realized along that traveler's path. This is where complementarity and relational thinking enter. Complementarity says that different observers can hold descriptions that cannot be combined into one global story and still be right for their own experiences. Relational quantum mechanics says properties have meaning only in relation to an observer or a system acting as one. Together they suggest there may be no single interior to draw as a universal map. Two black holes that look identical from far away could present different internal narratives to different infallers at different times. Even the same hole could yield distinct, consistent experiences to different observers, each carving a personal slice of space-time through the web of quantum relations. Some ideas go further and tie space-time itself to entanglement, the deep quantum link that correlates systems across distance. If geometry emerges from patterns of entanglement, then observing does more than find what is there. It helps assemble the stage on which events occur. Under the most extreme conditions near horizons, in high curvature, the dependence on those patterns should be strongest. That would explain why there is no finished atlas of a black hole interior. The place is not a fixed container waiting to be charted. It is a process, a network of relations that hardens into a particular history when specific interactions happen. Time follows suit. From outside, a horizon looks almost frozen. From inside, time can still flow, but not with one global clock. The order in which events settle may depend on the interactions that define them. That does not mean anything goes. It means the cosmos keeps time with local rules set by geometry and measurement together. The result is a lawful yet flexible script where the sequence an observer records is stitched from the relations they enter into. If our entire universe sits inside a black hole's interior, a new layer of questions appears. What lies beyond our cosmic horizon, and what sort of outside framed our beginning? In a parent cosmos, a massive collapse might have produced a black hole whose interior inflated into our space-time. To an external astronomer in that parent world, the black hole would look ordinary, dark, compact, slowly evaporating. Inside, a full sky would unfold, galaxies forming and fading, stars living and dying, chemistry and life developing as eons pass. Time rates could differ wildly between parent and child. Billions of years for us might be a blink for them. Do traits pass from parent to child? Some thinkers say yes. The spin of the parent hole could imprint a small global rotation on the child. The mass could set the initial energy density, and other conserved features could echo as boundary conditions. That would make every universe a child with family traits recognizable, yet free to grow in its own way. It also allows the parent to be very different. Its laws could favor larger stars, easier black hole formation, or unfamiliar kinds of matter. To its inhabitants, our constants and particle mix might look exotic. Seen in this light, black holes are less like bottomless pits and more like deep workshops. Quantum layers, tunneling routes, observer-shaped geometry, and inherited traits together outline a richer interior than the simple collapse to a point story. Whether nature chooses fuzzball-like surfaces, loop-induced bounces, layered mazes, or some synthesis we have not yet written down, the through line stays the same. Information, time, and geometry keep working under pressure. The hardest parts to see what lies behind the horizon, what happens at peak density, how a new region starts, are exactly where those rules must be tested most carefully. If a parent universe held countless stars, many would end as black holes. Each deep collapse could seed a child cosmos. Ours might be one among vast numbers, each with its own start, its own pace, and its own balance of matter and light. A parent world could be a broad nursery, rich in unfamiliar structures and perhaps forms of life we would not recognize. Or it could be gone, its history finished long ago, with only its offspring left to carry forward. In that view, our universe is a fossil of a larger event, moving on through its private time. Because our universe also makes black holes, we may already be parents. New interiors could be budding now inside the horizons we map around distant galaxies. The result is a branching family tree, not infinite in one shared space, but unending in many spacetimes, ancestors and descendants linked by collapse and rebirth. If this picture holds, the outside of our universe is not empty space. It is another universe with its own galaxies and rules. That universe may itself sit inside another, and so on. Whether this nesting ends in a largest outside, or rises without top or bottom, remains open. Our tools are forged inside this world. We cannot step out to check. What we can do is follow mathematics, build models, and watch the sky for traces that a simple, single universe story cannot explain. Dark energy is one such hint. The expansion of space appears to speed up, as if a gentle pressure pushes on the cosmos. Some speculate it could reflect effects from a boundary we cannot see, a pressure that belongs to a wider structure. This is only an idea, but it keeps the door open to influences beyond our horizon. The oldest light we can measure, the cosmic microwave background, offers other clues. Most of it fits a smooth, near-flat universe. Yet, there are marks that resist washing out. The best known is the cold spot, a patch of sky cooler than its surroundings by an amount that stands out when you map the whole field. At first, many blamed instruments or dust. After years of checks, the feature remains. Another surprise is a set of alignments in the largest fluctuations, a tendency to point along a particular sky direction when pure randomness would scatter them. Geometry could explain patterns like these. In flat space, light travels straight and never returns. In curved space, paths bend. In some closed shapes, think of a three-dimensional sphere, or a donut-like torus, light can loop and meet itself. That can imprint, repeats, or suppress certain large-scale variations. A space with negative curvature, like a saddle, tends to boost wide-angle differences. A space with positive curvature can mute them. Some of the actual anomalies look like muted large-scale power, which would be natural in a slightly closed universe. The cold spot might also have a local cause. Photons that cross a giant underdense region, a supervoid, can lose a little energy and arrive cooler. Surveys do find voids along that line of sight, but whether they are large and deep enough is debated. If not, curvature or early time effects may be at work. Either way, the patch keeps its place on the short list of cosmic puzzles. The alignment problem has earned a theatrical nickname, the axis of evil. It refers to a preferred direction in the largest CMB modes, confirmed by several missions. It could be a statistical fluke, or it could hint at a small global twist. If our universe was born from a spinning collapse, a bit of that angular momentum might survive as a subtle imprint, a fossil axis buried in the background. Polarization patterns add another layer. Polarization tells us how the early plasma in the universe moved and how space-time was shaped while light decoupled. Maps of this polarization show delicate swirls and alignments that do not perfectly match the simplest inflationary models. These mismatches might be noise. They might also be signs of curvature, rotation, or other structure inherited from a more complex birth. If space is finite but unbounded, there is no edge to hit, just as walking on Earth's surface never finds a wall. Yet if our universe sits inside a larger structure, there could be a special boundary in the deeper geometry, a horizon with rules of its own. That kind of boundary could bend light paths, smooth some fluctuations, and even create faint ring patterns through cosmic lensing. These signals would be very subtle. Next generation surveys, CMB-S4, Simon's Observatory, and future space missions aim to reach the precision needed to test them. Each improvement tightens the net around models of curvature and topology. Reading the CMB is hard. Foregrounds, noise, and instrument systematics pile up. Even so, the anomalies have lasted through better data and stricter tests. If we truly live in an interior shaped by extreme curvature, its fingerprints may already be in that ancient glow. The task is to separate durable signals from the clutter. A related question touches the foundation of physics, the values of the constants themselves. Our theories use numbers we measure, but cannot derive speed of light, strength of gravity, electron charge, masses of basic particles. Small changes to these values would erase stars, molecules, or stable atoms. The set we see looks tuned for structure and life. A family tree picture offers a way to think about this tuning. If every black hole births a universe, and each child rolls the dice on its constants within some range, most children will not support long-lived structure. A few will. Those few make many stars, and thus many black holes, and thus many children over many generations. Traits that favor black hole production would recur. This idea is called cosmological natural selection. It does not ascribe purpose to the process. It notes that reproduction plus variation leads to selection, even at the scale of universes. In such a scheme, our constants would sit in a region of parameter space that makes stars common, supernovae effective, and heavy elements abundant. Gravity strong enough to form galaxies, but not so strong that everything collapses too fast. Particle mass is balanced, so nuclei and atoms are stable. The result is not perfect fine-tuning by design, it is survivorship across many trials. None of this replaces the need for tests. The family tree view must meet the sky with predictions. Small global curvature, specific patterns in the CMB temperature and polarization, limits on how much rotation the whole universe can carry, correlations between black hole demographics and the large-scale structure we map today. The same goes for the idea that we live inside a curved interior. It must explain why most measurements look flat and only the widest angles misbehave, and it must do so in a way that tightens, not loosens, our overall fit to data. Taken together, these lines of thought point to a sober message. Our universe could be one of many. Its outside could be someone else's inside. Its oldest light could carry faint signatures of curved birth, and its constants could be the echoes of a history in which only some sets of rules make many stars, many black holes, and many children. The work ahead is to keep turning theory into clear, testable marks on the sky, and to read those marks with instruments, careful enough to tell signal from chance.